Welcome to this course on FPGA based signal processing systems. Today we will be looking at the simulation of combinational logic circuits. In continuation to this case statements, the syntax what we had learned that we would be making a model of this. There is a module which has this ABCSY with an inputs here, the ABC of 8 bits, and then a select line, 2-bit select line, which is also an input, and the output Y of 8 bits. So, from the input ABC, we are going to select a certain input and assign it to the output Y using the case statement, always at the rate of A or B or C or S. If you notice that A, B, C and S, those inputs are in the sensitivity list, they are listed, and this is a behavioral description because we use this always at a block case. The select comes here, that is what is the condition at which the case needs to be selected. The 2-bit, here you notice 2-bit D0, that is decimal 0 of Y, then if it is 0, that means the select is 0 0, okay. In binary, the input A is assigned to Y colon, Y equal to A semicolon, and if the case S is, yes, this is 2, if 0 1 or in decimal it is 1, Y equal to B. So, select B and assign it to Y. So, the input B is assigned to Y. So, you notice we are using the blocking assignments, okay, all of them are blocking assignments. And in the next case we also see them 2-bit 2, if the input, the cases, select line cases 1 0 2, then C, the input C is assigned to Y. So, there are 3 inputs only, but we have 2-bit select line which can have the combinations 0 0 0 1 1 0 and 1 1. So, in the other combination, that is the 4th combination, 2-bit 3, that is 1 1. So, assign 8-bit Z, okay, the high impedance state. So, this case is not available, but we need to give the, what is the, if select line gets into 1 1 1, what is this, what is that the Y needs to be, that should be told here. So, the default case, that is, it is mandatory to have the default case, otherwise it was, in synthesis process it would infer a latch. So, Y equal to 8-bit X, that means X X X X X. So, 8 bits unknown number or the don't care will be assigned to Y if the default case is Y. So, here what is the default case can occur, just let us look at it. S is equal to 0 0 0 1 1 0 1 1. If any other select lines, then it would be giving the defaults Y equal to 8-bit XXX. So, anyway, we have covered this here, the all select line combinations, and you would also notice this is not necessary to always write these cases or the choice in the binary. You can also represent it in the decimal. This is a behavioral description of selecting certain inputs among the 3 or 4 inputs and then assign it to a bus. So, then end case, it is a case and end case is mandatory. The end module is, I have already because when we start that we fix this end module also. So, this is the example of this case statement. And coming to the Verilog parameter declarations, though we have seen this already in the previous lectures. So, parameter declaration is, parameter is a keyword, identifier equal to value, fix the constant or assign a constant value to a identifier, and there are 2 formats. One is one value assigning to it, or multiple values can be assigned to particular their own identifiers using one parameter statement. So, here you need not repeat. If you want to assign 2 or 3 constants, then it is better to have this parameter one assign statement, that is parameter identifier equal to the first value, comma, notice the comma here, and identifier equal to second value, and so on, how many constants you want to define, and then final constant needs to be having the semicolon. So, this is the parameter declaration. So, we can see the examples. Suppose it is bus size of 32. So, here it is a comma, again you can see MSB bus size minus 1. So, because 32 minus 1 will be the MSB, and then LSB is 0. Okay, so the range of indices also LSB is different. So, multiple assignments can be declared in one statement. So, this is the parameter declaration can be done over two formats. One is that only each constant needs to be defined as parameter, otherwise in one parameter statement you can have the all of them defined. So, this is escape character is 7-bit 00011 and 011. So, this is again defining example of defining this parameter. You can also see the example with using the parameter, that is data flow model, which has set in the model name is PDF, P suffix df. Y is the output here, you can see that is single bit, and I0, I1, I2 inputs. Okay, in this case the output is you see the width parameter is defined width equal to 1. So, if width is 1, it is just we won't be going through this part of 0. If you see 1 minus 1, it will be again 0 colon 0. Okay, so the I0, I1, I2 will be 0 bits. So, within the bracket, square bracket, we have 0 here. So, that is showing that it is 1 bit. I0, I1, I2 are 1 bits. This is one way of defining this is 0 or a single bit number. So, y is also width is defined 1 minus 1 equals 0, that is y. Now, we see the assign statement y, which is equal to I0 and I1, okay, and logic I0 and I1, and I0, I2, I1, I2, and OR them. So, it's just a logic circuit which have y of ANDing I0 and I1, I0 and I2, I1 and I2, and then OR them in one single statement. So, just to illustrate that the width bit can be anything. Here you can use this I0, I1, I2 as 2 bits, and then use this width as 2 minus 1, 1. So, y can be 2 bits, and I0, I1, I2 can also be 2 bits. This is for the single bit example using this parameter declaration. So, the end module, and along with the input output declaration, you define the parameter also. So, now let us take the if statement. How do we use this in the Verilog modules? So, the prime number detector module, which has the module M, the PND with module name. M is the input and F is the output. Here the logic circuit which we are dealing in the previous lectures also, you can just recall that. And input is 0 to 3 M, there are 4 inputs, 4 bit input, and then F is the output, and you know the meaning of the range now, and parameter also. The parameter is prime equal to 1, it is the prime is assigned a value 1. Okay. So, now always at the rate M, specify if M equal to 1. If M is equal to 1, then F sign equal prime. Okay. So, 1 is considered prime number. So, that is why if it first checks this, if M is coming to be. So, M is the input which is in the sensitivity list also. So, if M equal to 1, assign that F equal to prime. Prime is initialized to 1 here. Now, else if check this other conditions of the input, that because it is a 4 bit input which can have 0, 2, 4, apart from 1, 0, 2, 4, 6, 8, 10, 12. Else if check the condition, if this is the first condition, else if the second one is M percentage 2, which is mod operator here, it is if it is giving 0, the remainder equal to 0, that means it can be the M can be 0, 2, 4, 6, 8, 10, 12 and 14. In that case, begin and end. That is within the statements this are within the begin end block. Okay, so again check this among this, if these numbers come and those are giving the remainder as 0 because these are divisible, yeah, with 2. So m equal to 2, is it 2? Checking here, condition of m equal to 2, else yes, then f is 1, it's a prime, else all other things, that is 4, 6, 8, 10, 12, 14 and 0, all are 0. Okay, so if has this else in the begin block, that's no issue, and this if f equal to prime, else if we check this condition all of them, and then now we have done 1 and 2. Okay, so these other non-prime numbers are taken care of. So what about the other one, else if m is less than or equal to 7. Okay, so less than or equal to 7 again comes 0, 1, 2, 3, 4, 5, 6, 7. So these conditions other than 3, 5, 7 are considered here. Okay, so if this 3 comes, then f equal to 1. These are prime numbers again. Now coming to the rest of them, else if it is 11 or 13, give 1. The logically if these are equal, either of this, then this condition is satisfied, f equal to 1, or else can occur only in 9, then it is f equal to 0. So it catches up all the combinations of the 4-bit inputs, this program, and you see the if else structure. This is a priority structure. If first it checks for m equal to 1, next it checks for these cases, and then next it checks for m equal to 2. Okay, again then else if m less than or equal to 7f. Okay, so it's not a concurrent statement within the always block, these are sequential. So one by one this is getting executed. So this would form a in the synthesis process, this if else if statements or if else statements form a priority structure. Okay, not a mux structure in the synthesis. But if you have mutually exclusive conditions of this, mux would the structure would be synthesized as mux, but here is the priority structure. One by one it checks for if else, and then it satisfies this else also. If none of them is true, then else f equal to 0. So there won't be any latch formed during the synthesis process, latch inferred in this case, but this is a priority structure. So using the if statement, this is an example of the prime number detector. So now coming to the for statement, here for loop index equal to first expression, and then logical expression, loop index equal next expression, and procedural statements would follow. This is one format, and we have the other format, loop index equal to first and loop index less than or equal to last, loop index equal loop index plus 1, or this can be, if these two are interchanged, it can be a negative also, loop index minus 1, as in the case of any other software languages procedural statement. So this expression can also be defined, first expression, and then what is the next expression, I plus 2, or okay, and then what is the logical expression to be satisfied. Okay, so this is another format. So this is usually in the practice we use it, loop index equal to first, loop index less than or equal to last, and the 0, it can be 0, and the less than or equal to last will be 255 or 127 or 128, whatever, and the loop index will be increased to plus or minus plus 1, or it can be 2 also, or it can be of any number. This can, if it is not 1, this can fit in here as well. So these are the two formats used. So let's use the for statement for the this prime number detector module. Again, this PND with m and f. So input, now considering this 16-bit input instead of a 4-bit input, because we are going to use the for loop and to check it exhaustively, that 16-bit, it can be even 0 to 3 as in the previous case, but f equal to output, reg or f and prime, notice here, and integer I, these are the new things. So output is declared as reg, that's fine, and you see the prime always at the rate m, that is input begin, and prime equal to 1. So prime is declared here as 1. You can see it is initializing here. We have initialized in the previous example over the parameter prime equal to 1. Okay, so here it is inside the always block. Okay, so it is visible only inside the always block. So this needs to be declared as reg over here. Okay, so f, and but f is used inside the always block, also it is the output. Okay, so that's the difference between f and prime. Okay, prime is visible only inside the always block. Okay, prime equal to 1, that's an initial value. Next, if m equal to 1 or m equal to 2, that is just a checking special cases, prime equal to 1 and 2 are satisfied. If either of this comes in, else if m is again the same condition which we have used in the previous example, m percentage 2, it's 0, then prime is 0. Okay, it's not, those even are not prime numbers. And then coming to the other conditions using the for loop, for 1 2 is considered, and then 3, so I is starting with 3, the initial value, and it goes up to I less than or equal to 255, and the next expression here is loop index is iterated with I equal to I plus 2. So 3 5 7 and so on up to 255. Check this also, if in this for loop when it is doing this, next is needs to be checked, is it divisible by I, m is divisible by I. So 3 by 3 is divides, m is suppose 3 and divisible by 3, it's giving 0, and m is not equal to I, 3 is not equal to 3 here. So this condition, so 0, it is 0 if m is divisible by any I. Okay, so suppose I is 4 or 5 is 5, so in that case, is it divisible, check it, and then if it is divisible, that's not the prime number. So prime equal to 0. So now we have in this always block, we are just updating the prime only. If you look at the previous statements as well, prime equal to 1 if 1 and 2 prime, and now the prime is declared in within the always block, but output is f, prime needs to be transferred to f. Okay, so the next step what we do here is that if prime is 1, all of the cases of 1, f equal to 1, else f is 0. Okay, so this is to taking the output, so end. Okay, so just to give there is a variable which is declared inside the always block, we have seen in the examples also. This is a behavioral description of a combinational logic. Okay, so here it is extending this prime number detector to up to 255. Okay, so 16 bits. So you can have this even more numbers, and depends on the input size, you can declare that. So the next, this is one example of the for loop. So prime number detector we had seen in the if state, using if statement and the for loop as well. We have also used this assign statement, simple assign data flow model. These two are the behavioral description. So using for loop again, so counters. So counters are mainly used in the design. So how do we use the for loop for the designing the counter? So integer count. So integer declaration, I think now it is understood that we have in the previous example also, the I in the for loop is declared as integer. So this is a count integer. I am not giving the module here. So this initial, which is executed only once. This can be used even in the case of test benches. So for loop count equal to 0, and then count less than 128, count equal to count plus 1. Okay, so here is we have the for loop structure. So similarly here we have count and then less than or equal to count, then count equal to count plus 1. So we have this count will execute up to 127. Okay, so the count will be increased to count plus 1, 0, 1, 2, 3 and so on. So the display is within the bracket, we count percentage d, count equal to percentage d. So display it in the decimal count. Okay, count first is 0 and then 1, 2, 3, 4 and so on up to 1, up to this the condition of this is met. So 0 to 127 can be met. This is the you can use the for loop for generating the counter behavior. So now the some of the loops, other loops, repeat loop, while loop, and then forever loops. Okay. So repeat, what is the syntax for it? Integer expression. Okay, repeat how many times. Okay, so it's going to be an integer expression, and do the rest of the thing, the procedural statement. Once, how many times you have to do the description what is given in the procedural statement. And then next comes the while loop logical expression. What is the condition at which the while loop should be executed? And then while logical expression, procedural statement. There's a list out the procedural statement next. This is a syntax within the bracket logical expression. Here it's an integer expression. Forever loop, forever, what is the procedural statement should be executed. Okay. So we'll see some examples of this loops 1, 2, 3. While loop, integer count, the same example of counter. Here is initial begin count equal to 0. First initialize it to 0, and then while, what is the logical expression needs to be, so count less than 128 up to 128. In the for loop what we have used, count less than 128, this loop will be executing this up to 127. Okay. So or you can write less than or equal to 127 also. So that is also fine. Count less than 128, begin here dollar display that count d is equal to count. We are displaying it first, you see, and then display the count variable. Next we go to the count equal to count plus 1. So increment it end and end. So here is the count is incrementing. First it displays the 0 using this previous it display while the first count while count less than 128, yes, and it the initial value is 0, 0 gets displayed, and then the count is increased to 1, that is 0 plus 1, and then in the next while it is 1, the display gives 1 and then increment it. So in this way this is going up to 127. So the counter goes up to 0 to 127. This is the logical expression you can notice in the, this can be used in the test benches. So that repeat loop, again using the counter with the repeat loop, integer count, initial and begin end. So count made it 0. Here we have the multiple statements in the initial. So we have this repeat loop, repeat and then 128 times. So repeat this 128 times, begin end. So display this and increment it, display and increment it, so that it can go up to 0 to 127. So here the first one, it starts from 1, 2, 3, 4 and 128 times it is getting repeated, these procedural statements getting repeated. Okay. So it would display one up to 0 to 127. Okay. So there is this repeat loop. So don't forget to initialize this counter variable. So these are up to the using the for loop, while loop, repeat loop, and then how do we use the generate the clock signal using the forever loop. So module clock generation, can say reg clock, initialize this clock at time 0, that is t equal to 0, initial clock is 1 bit 0. Then you can say the toggle, use this always block, and then we'll go to the forever also. Always, how do we generate usually the clock signal here? So here, so the clock signal of, okay, so this is the time period, right, of the clock. So what we say here, this clock, the signal is called as a clock, it's a variable. So don't forget that to declare it as, this is in the test bench anyway. Clock is a reg, and this clock is used inside the always block. This needs to be declared as reg here. So the always hash 10, that's a new one, or this is the hash indicates here, it is the time information of the, which is 10 time units. Clock is equal to clock, not clock. So the not clock, when initially it is 0 and then it becomes 1 when after 10 time units. So first initially 10 time units it is 0, after that it becomes 1. Okay. So then this is the always statement, you can see without any sensitivity list. Okay. So the always can be of two formats. It can be used in the two formats, always with sensitivity list. If there is any change in the signal of this sensitivity list signals which were listed, then the block gets executed. Here this is without sensitivity list. Always the time delay can be mentioned, the time 10 or something, whatever. Clock is not equal to not clock. In that case, 10 time units it is 0, 10 time units it is 1, and then again it repeats 10 time units and 10 0 and 10 time units it is 1. So this continues without any condition always. Okay, so there is no condition specified where to stop. So that's why initial hash $1000 finish. So specify after that 1000 time units. Okay, finish this. Okay, otherwise it would keep continuing if you don't use the dollar finish at this point. So the clock period is 10 your time units plus 10, that is 20. That's time period will be 20 time units. Suppose it is nanoseconds, it will be a 20 nanoseconds clock. Okay. So this is a method of generating the clock using the always block. So this is the key statements used for generating the signal, because this we will be using it in the sequential circuits. Okay, so sequential circuits needs clock. So when we design the sequential circuits, the clock needs to be generated. That is usually generated in the test bench and given to the Verilog module. Or if we consider the real time, if you target the FPGA, this clock signal is already available in the board. We will be using that pin in our constraints file and feed it to the module. So this is the clock generation with the always block. So forever loop, which we had seen, clock generation, use a forever loop instead of always block in that. So reg clock, initial begin clock, assign it or initialize it to 0, then comes forever hash 10 clock equal to not clock. So clock period is 10 unit, 20 time units, because it is 10 time units it is at one state, and then another 10 time units it is in the next complemented state. So hash 10 always delays this this evaluation and assigning. So we will see delayed evaluation and delayed assignment, all those things when we deal with the timing controls. So right now we have put the hash 10 before the clock equal to not clock. So this will be continuing forever. There is no stop here as well. So it's we can have initial and then at some point of time dollar finish. Okay, otherwise it would continue. This would also keep continuing. So we'll be stopping at some dollar, some hash 1000 initial, hash $1000 finish. Okay, and then in the sentence needs to be added for stopping the clock at some place. This is an example for the forever loop. So while loop, repeat loop, and then forever loop, for loop. So these examples we had seen. So now one or two examples of the net types what we had learned, if you recall, in the structural type, structural combinational logic, we have seen the wire and the trie. Okay, so trie we used in 2 to 1 mux, and wires are being used in other structural models. So now if supposing the net type is trie and wire and trie or and wire or. Okay, so what are the logics it is following? So net, so in this case these are multiple drivers having the multiple driver. So driver 1 and driver 2. So that means if you have a variable y which is driven by 2 signals. Okay, so in that case what happens, how the driver 1 and driver 2. So in that case net value becomes 0 whenever any of the drivers output is 0. So if two drivers are used, if one driver is giving 0, then all other, I mean either it is wire and or trie and, that will be 0. Okay, that's what. So if in this case also all of them are 0, so one driver is 0, other driver 0 1 x z, it is giving this. So the inputs these two combinations result in 0 0 0. Also, both the high impedance state is also allowed in the output. You can see it's not in the case of other gate logic built-in gates what we have studied. So, the output is Z here, and the remaining, if it is 1, it is 1, and here going to be unknown, 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 and 1 Z also 1, and 1 Z also it is going to be 1. So, this is the truth table for tri-AND or wire AND. And similarly, if you have tri-R and wire R, net value becomes 1 whenever any one of the or driver outputs 1. So, here driver 1 and driver 2, tri-R and wire R, 0 1 x z. If it is 0, yes, it is going to be 0, because it is an OR function only, 0 1 0 0 0 x 0 0 z 0. Okay. So, and then the OR values again. So, if any one of this is 1, so in this case it is 1, you can see, and similarly if any one of 1 is 1, in all these other combinations it is 1. So, z is allowed, remaining gives the 0 here, and then the unknowns or they do not care. So, let us take this and see one example for this tri-AND, wire AND, tri-R and wire R. So, net type it's demo, that is you can take wire AND. So, how do we declare this wire AND W AND a variable, whatever this is your choice, and these wires A and B, A1 B1 are wires in this. So, now we are assign 1 bit to A1 1 and 1 bit 0 to B1. Okay. So, now assign wire AND this wire you can see that is declared as wire AND A1 and the same wire AND B1. So, A1 and B1 if you assign it, what would be the wire AND, because these are concurrent statements. Okay. So, what would be the wire AND A1 and B1, A1 is 1 and B1 is 0. Okay. So, let us see, so the any one of these signals, let us see the output also similarly. For that wire R, what would be the output? I will give you this here. Wire R, similarly wire R, declare this W R and wires A2 B2. Okay. So, assign A2 is 1 bit 1 and B2 1 bit 0. The wire R is assigning A2, assigned A2 and wire R is again assigned B2. So, in this case what would be the wire R? Okay. So, following the our truth table, so 1 and 0, this is again what would be the output. So, similarly the third tri-AND example. So, the T AND is declared as tri-AND. T1 and T2 are the other two signals declared as wires, and reg enable 1 and enable 2 which is required. T1 and T2 are 1 and 0, and similarly this T AND enable is 1 is true, T1 assign T1, otherwise 1 bit Z. Similarly, T AND if enable 2 is true, T2 assign or 1 bit Z. So, in this Z is allowed in this case when you define tri-AND at tri-R, similar to the tri-R also T3 and T4 enable T3 T4. Okay, tri-R. And so, now we are going to see the output. So, display this all of them and more dollar monitor wire AND, wire R, T AND and TR, and time also. Enable is 1 and 1, 1 and 2. Okay, so in that case tri-AND and tri-R, in the examples both drivers are enabled 1 and 1. So, that means in case T1 T2 T3 T4. Okay. So, in this for hash 10. So, similarly enable 1 and enable 2 in the test bench, that is only one drives here, and if this is 0 1, again this is 0 drives, 0 0, none of them drives. So, dollar finish, what would be the output? Let us see here. The outputs are specified here. First case is at 0 0, the wire AND 0, wire AND gives this is wire AND, wire R, tri-AND and tri-R. Okay. So, the first case at 0, so it is giving 0 and that is 1 and 0 1. Okay. So, AND function and OR function is executed anyway in both cases. So, it is going to be wire AND and wire R, So, this is 0 and 1, tri-AND is 1 and tri-OR is 1. At this case it is we have changed it. So, here 0 1 0 0 and both cases are not there, then it is going to be resulting Z as well. Okay. So, now looking back to this one, in this case, go back to this. So, here 1 and 0 AND function A1 and B1, so wire AND will be 0 because it is wire and logic of these two signals wire AND is getting, so it is going to be 0. Okay. In the second case, OR function 1 0 0 plus 1 and it is going to be 1. And then in this case, when you declare as tri-AND and 1 and 0, okay, so if enable is 1, so and enable is 2, T1 and T2 are 1 and 0, so this is an AND function, this would be 0. Okay, so the 1 and enable is 1, enable 1 is 1, enable 2 is also 1. So T1 should be assigned here, T2 should be assigned here. So T1 is 1 and T2 is 0. Okay, so in that case the AND function of this would be assigned here. And the next case, if it is 1 0, okay, 1 0, then T1 will be 1 and this will be Z. Okay, so 1 prevails in that from the truth table, and so here 1 T3 T4 similarly. So you can see the outputs, only one drives here, 1 and 0. If this is 0 and 1, then 0 will be prevailing. So what is the value of 0? 0 0, there is a high impedance state. So you can compare this with the outputs what we have got, 1 1 and 0 0 0 1. This is for wire AND and wire OR. So this is giving you all the three are same, whereas the change you can observe are these combinations. This can also be viewed here at 10 and then next at 20 and at 30. Okay, so this representing in picoseconds, that's why we are seeing this 10,000, 20,000 and 30,000, but hash 10, hash 10, hash 20 and hash 10 is given in the circuit. So every hash, every 10 units of time it is getting incremented. So you can view the corresponding T AND, W AND, W OR and also TR. So we should note down wire AND, wire OR can have continuous assignments. Okay, so tri-AND, tri-OR also dependent on enable signals and the Z is supported in the output. Thank you.